Ladies and gentlemen, welcome to my lecture on multiple equation models. This model framework is often denoted as seemingly unrelated regression technique, which is often abbreviated as SUR, SUR technique. So when do we use this technique? So if we have many equations, let's say in financial economics, in the context of asset pricing, you might have heard about this so-called GRS test. The GRS test is an hypothesis test where you test the intercept terms of multiple equations of test assets that are regressed on a risk factor pricing model. And what you do in this test is you test those intercept terms of test assets jointly. And in this case, you would, for instance, use the seemingly unrelated regression framework. So how does it look like? So first of all, in this case, we operate with only two equations in order to keep things simple here. So the first equation here, we have a random variable, the dependent variable, y1t. So y1t, we denote it here. So yit is what? It's the excess return of asset I at time t. Just to give you an example. So y1t, so the excess returns of the first asset at time t are dependent on a factor model. The x variable, what's x? The x variable at time t, it is the excess return of the market factor at time t. If we are in the US, for instance, we would use the S&P 500, for instance. And note again that we have the assets, test assets, and the market factor here in excess form. So basically, that's the standard CAPM framework. And in doing so, we include an intercept term denoted here as alpha 1. Moreover, since we have a regression framework, we know that we have to add a residual term, denoted here as epsilon 1t. It's the regression residual of the first asset or the first equation at time t. And once again, for my courses, you need basic econometrics. So you have to be familiar with standard OLS regression models. And of course, the underlying statistical theory behind it. So next, we have another asset denoted as y2t, and y2t is in this model dependent again on intercept term denoted as alpha 2 plus beta 2, which is the exposure against what? Against the market factor xt, and also we add again here an error term. So we have here two equations. If you read the papers from Pharma and French, they usually use 25 test assets. So you would have here 25 of these equations. But we keep things simple. We just consider two assets and the market factor, only one factor. So obviously we could also extend here. We could have more regressors here. So we could have the Pharma and French 3-factor model as an example. Then we would have here an additional factor. We would have here an additional factor which has also a separate exposure. We could then have, for instance, we could denote x2t would be the SMB, the size factor at time t. We would have a third variable, let's denote it at x3t, which could be the value factor, HML factor, high minus low booked market ratio, and so on. So we could extend these models here however we want. So it's the idea, the basic idea is exactly the same. So what else can we say? So first of all, we have capital K. K is 2, and K measures the parameters per equation. So in each equation, we have the same amount of parameters. So in this simple framework, we have two parameters: the interceptor, the regression intercept, and the exposure against the market factor. And this we have for both assets. So capital N is 2, and capital N gives us the dimension of test assets. Yeah? So it's very simple here, and as we just said, N could be also 25. Yeah? And if we have the permanent branch 3-factor model, yeah, we would add 2 parameters, yeah, and 2 regressors. So then the parameter space would be K is 4. Yeah? Just as an example. Moreover, we can give these equations here, we can give them also as a representation in matrix using matrix notation. Then obviously y1 is a vector. It's a t by 1 vector. We have capital T time series observations. So and for each variable here. So for both test assets and also for the market factor, these guys are t by 1 vectors. And from linear algebra, we know this notation. M denotes a matrix, and t by 1 would be the dimension, and we know a matrix t by 1 is simply a vector. So in matrix notation, our y1, for instance, which would be the vector for the first test assets, would be then just collecting the corresponding time series observation of the first test asset and would stack it into a t by 1 vector. So very simple. And of course also the residual terms here, once we have estimated the model, they will be also t by 1 vectors having the same equation, having the same dimension as the dependent variables, of course. So again, K is the parameter space. We have, and also what's also important to know, usually when we have the seemingly unrelated regression model, we have the same regressors in each equation. So that's also one thing that is important to bear in mind. Otherwise, we would need a different methodology. Okay? So why do we need seemingly unrelated regression model? So why can't we just use OLS regression? So the point is, we use this methodology always then when the assets on the left-hand side, so the dependent variables, are correlated. So we could also here have certain industry assets, and we know also that industries are also correlated. So that's why we would use this method here. So we can also show it by having a look on the covariance matrix. So if we define the parameter space of our model as phi, we can stack all the parameters into a 4 by 1 vector, or it's in essence capital N times K by 1 vector, and we know capital N is 2, K is 2, so it's a 4 by 1 vector. And we stack just the parameters from each equation into a column vector and denote it as phi. So that's this vector here, phi, captures the parameter space. So what's the covariance matrix of this vector phi? It's obviously a 4 by 4 matrix. It has to be like that by definition because the covariance matrix is symmetric. And we know what is on the main diagonal. So on the main diagonal, we have the variances of each single parameter. Starting here with the variance of the first guy, this alpha 1, moving on to the variance of the second guy, which is beta 1, and then we go to the next equation and collect those variances on the main diagonal as well. Above and below the main diagonal are obviously the covariances between these parameters here. And that's now the point here. That's exactly the point. So if the left-hand side variables are correlated, then here there will be something on the covariance on the above and below the main diagonal, because that means that there are some covariances that will be unequal from 0. Because if they would be uncorrelated, then we would have above and below the main diagonal, or we would have the elements of the first equation here. This guy is alpha 1 would be uncorrelated with this guy here, alpha 2. And as well, alpha 1 would be uncorrelated with beta 2. But if there's a correlation going on, we can't say that. Yeah? It's possible that these guys here are correlated, so between equations. And alpha 1 can also be correlated with beta 2. So we have to account for the correlation structure between the parameters, because they will enter the test statistic. And that's the important point. That's why we need this simultaneous equation model denoted here as seemingly unrelated regression technique. Yeah? So in empirical asset pricing, what people are often interested in, they have a pricing model. Yeah, and again, in our case, we have just a simple one-factor model, the CAPM, but we can easily extend this model. Yeah? What we are interested in, if the model, yeah, the variables here on the right-hand side, can they explain, or can the exposures against the factors here, or the variables on the right-hand side, can they explain the evolution of the test assets? If so, then the intercept terms here, alpha 1 and alpha 2, should be statistically not different from 0, jointly, at the same time, both. So that's basically what the GRS test is all about. And of course, we can test anything in this framework here. We could also test, we could be interested in testing if the exposures against the market factor are significant. Yeah? So what would this imply? So let's say you might have heard about the Farmer-Macbeth regression framework. In this model framework, you are interested in evaluating whether the betas, the variation in the betas, if they explain the variation in the sample averages of the test asset. Yeah? So do the variation in betas, do they explain the cross-section of expected returns? Yeah? And the expected return is sample average of each test asset. So you might guess if those betas here are in this time series framework, if they are jointly statistically significant, if that is the case, they will be also, or they must be per definition, if this matters here, if the exposures are significant, then obviously it has an impact. So in this case, we would expect that also in the Farmer-Macbeth regression, that this market factor is priced. Yeah? So we can basically do a similar test as in the Farmer-Macbeth framework, where we consider the cross-sectional effect. We can do the same thing basically here in the time series framework, yeah? Testing jointly the exposures against the risk factors if they matter. Yeah? And usually time series tests are stronger tests than cross-sectional tests. Yeah? So you might remember, if you are familiar with Farmer-Macbeth regressions, that we have a bias going on. So we have to use this so-called Shanken correction, because the Farmer-Macbeth framework is a two-step procedure, yeah, and we use the estimates from the first step in the second step. Yeah? But because we are using estimates, that they can be, we have to account for that, and that's why we use the Shanken correction, yeah, which makes the covariance matrix for the corresponding t-statistics bigger, and that's why the t-statistics will be lower. We talked about that already in another lecture of mine. So let's go back here to the pricing test, this so-called GRS-test, yeah, that you often hear in asset pricing research. So let's say we want to test if the intercept terms here, are they jointly statistically significant? Yeah? So under the null hypothesis, they are 0. We assume that they are 0. If we reject the null hypothesis, then we know that this model here, the CAPM model, is not able to explain fully the excess returns on the left-hand side jointly. Yeah? So in this case, you would reject the CAPM model as an adequate pricing model for pricing the test assets. So under the alternative hypothesis, so at least one of the alphas here should be unequal to 0. And we write it like that: alpha I is unequal to 0 and I is 1 and 2. Yeah? Simply because we have the dimension of our parameters that we want to test here is 2. So obviously, if we would have 25 test assets, then we would have here 25 conditions, yeah? And we would have here, this guy here, I, would be then from 1 to 25. What else can we say? We can stack we can give our null hypothesis as well in the matrix notation. So we can stack those parameters that we want to test into a vector. Since we have two equations here and we want to test two parameters, each one parameter per equation, it becomes a 2 by 1 vector, alpha 1 and alpha 2 in a 2 by 1 vector collected. And the alternative hypothesis, or the null hypothesis, it should be equal to 0. Yeah? The parameters should be equal to 0, and we can denote this as Q. Yeah? Q is basically what we expect under the null hypothesis. And Q is, again, it's a 2 by 1 vector. Yeah? It's defined as a 2 by 1 vector. So now we have to know that the test statistic in this joint framework, because we're not interested in one single parameter. If we would be interested in one single parameter in one equation, we could use simply the t statistic. But now, if we test more than one parameter at the same time, jointly, then we need to use a different test statistic. And this test statistic in this framework here is chi-square distributed. And since we have two parameters that we want to test under the null hypothesis, this corresponding test is distributed as chi-square with 2 degrees of freedom. Yeah? So if we would have 25 test assets here and you would want to test 25 of the intercept terms, then obviously this guy here would be distributed under the null hypothesis as a chi-square distribution with 25 degrees of freedom. Yeah? So the test statistic, it looks quite fancy, but that's just how it looks at the first glance. So in the end of the day, what we will do is we will step by step break it down, and then we will basically put everything together. So what is it defined? So it's basically a matrix capital R times beta hat, and beta hat here is basically our phi. It's a capital N times k by 1 vector. Yeah? So this guy here is n by k, capital N times capital K by 1 vector. So we subtract from this matrix product here what is our null hypothesis, our Q vector. Yeah? So what is here, in our case, what is here, this thing here must have the dimension 2 by 1. And because it's transposed, it becomes 1 by 2. Yeah? Note here that we have the transpose sign here. So this guy here becomes 1 by 2. So what we have here again we have a matrix product. So we have the matrix capital R that we have also here, and we multiply it with something in parentheses here. And what is that? It's a matrix X with a wave on it, transposed times what? Times a matrix sigma hat. It's the estimated covariance matrix of the residual term here, inverted. This is the Kronecker product, the Kronecker product, and this is the identity matrix that has the dimension capital T, because we have capital T time series observations. So again, we multiply this expression here with the same matrix like here, X wave, close the parentheses, and multiply it with the matrix R from here, transposed. And the whole term here will be inverted. So this whole term here must have the dimension, as we will see, 2 by 2, if we have multiplied it out. And then we have to multiply it again with what? With the same thing that we have here on the left-hand side, and that has the dimension 2 by 1. Note now, again, here it's transposed, that's why it's 1 by 2. So what comes out is a number, of course. So everything multiplied out, will give us a number, and that's a random variable, and this random variable is under the null hypothesis. If the null hypothesis is true, this guy here will be chi-square distributed with 2 degrees of freedom. So the number that comes out of this product here, we have to compare it with the critical value of the chi-square distribution with 2 degrees of freedom in order to evaluate our null hypothesis. So what we have to do now is we want to break down each of these matrices in order to be able to compound the corresponding value of the test statistic. So let's start with sigma. This matrix sigma hat, and which is here in this equation here inverted. So let's start with that guy. So what is sigma? Well, first of all, we have to run 2 OLS regressions for each single equation. So that's basically how everything starts. We have to define our regressor matrix, and the regressor matrix is the same for each equation. We talked about it already. And what do we have? So in our regressor matrix, we have a vector of 1s that will give us in the estimation the corresponding point estimate for the intercept term, and we have the market factor here. A vector of x, x1, x2 until x capital T. So the regressor matrix for each single equation here has the dimension capital T by 2, of course. So then again, we know from OLS regression the corresponding point estimator for the first equation here is then given by what? It's the regressor matrix X transpose times itself inverted times X transpose times Y1, times the vector of excess returns of the first test asset. So what we will get then are the corresponding point estimates. We know the dimension must be 2 by 1. Our B1 hat vector has the dimension 2 by 1. It gives us the corresponding point estimates for the first 2 parameters of the first equation. So we have to do the same for the second equation. So everything, the regressor matrix is the same. So we do the same regression, but we have to use here as regressand, we have to use the vector for the second test asset, which is our y2. What we get then in turn is the corresponding 2 by 1 vector of that collects the estimates for alpha 2 and beta 2 here in the 2 by 1 vector, denoted here as B2 hat. Again, if we have 25 test assets and the cap n, obviously we have to do this 25 times. And we get 25 parameter vectors bi. Very simple. So next, we know from our standard OLS framework that the estimated residuals are then given by what? It's given by the corresponding vector of dependent variables y1. So for the first equation, the vector of regression residuals is then given by y1, the vector of excess returns for the first test asset, minus what? Minus the regressor matrix times the estimated parameter vector. So this gives us the part of the excess returns of the first asset that is unexplained by that model here. So our epsilon 1 hat is a t by 1 vector. It stacks us the regression residuals for each point in time into a t by 1 vector. Okay. At the same time, we will also get the residual vector for the second test asset, for the second equation here. It's then given by what? So our regression residual vector epsilon 2 hat is given by what? By y2, the excess return vector of the second test asset minus the regressor matrix X times the estimated parameter vector. So now we have the residual vectors for all equations. Given that, we can compound the corresponding estimated residual covariance matrix denoted as sigma hat. And what's that? Well, we simply multiply this vector here for the first test asset. We take the residual vector, multiply it with itself, transposed. Yeah? So t by 1 becomes 1 by t vector times the t by 1 vector. So that's just a number what comes out here. It's a scalar product, okay? And we divide it by the number of time series observations. And that's then the corresponding residual variance of the first equation or the first test asset in our context. The second element on the main diagonal is what? It's the same thing, just we use the residual vector from the second test asset or from the second equation. It's our epsilon 2 hat transposed times itself divided by the number of time series observations. And that's then the residual, the estimated residual variance of the second equation here. And what's above and below the main diagonal? Well, it's the epsilon 1 hat transposed times epsilon 2 hat. It's the covariance. And we have to divide the scalar product by the number of time series observations. We do this for all elements here. And that's then obviously the covariance between the residual covariance between these two test assets here. So that's the important point. We don't get that if the test assets here would be uncorrelated, then we would have here 0 on the main diagonal. Okay? Yeah, sorry, we would have a 0 above and below the main diagonal, of course. So the residual covariance matrix, given that we have two equations here and two parameters to estimate, it's a 2 by 2 matrix, or an n by n matrix. If we have 25 test assets, then obviously our residual covariance matrix must be 25 by 25. So that's the first step, and let's move on. So what we have now realized is that we know how to estimate the matrix sigma hat, and here in this expression here we have to transpose this guy, and this is luckily something that any computer program will do by command, at least most standard programs. Okay, so we know now this guy here. So what's next? The question arises, what about this beta hat? So beta hat is nothing else. We know already it's this phi vector. It stacks basically just the corresponding parameters of each equation into a capital N times capital K by one vector. We know that from the previous derivation, we know that our B1 hat is the corresponding are the parameter estimates for alpha 1 hat and beta 1 hat, and B2 hat are the corresponding point estimates for alpha 2 hat and beta 2 hat. So our beta hat is basically just a 4 by 1 vector that stacks these elements here, equation for equation, into a corresponding capital N times capital K by one vector. Very simple. So now we know also what is this guy here. Our beta hat appears obviously here and here in our test statistic. So what's next? We have also this capital R matrix that is here. We have it 4 times in the expression for the test statistic. So what's that? What's our capital R matrix? Well, let's say that we have this our vector of point estimates beta hat. Then our R, it should give us for each equation the corresponding, it should indicate where to find the corresponding parameter estimate that we want to test. So as of now, we're interested in the intercept terms. And in this vector here, in our 4 by 1 vector, it's obviously the first element here, and it is the third element here. Yeah. So we multiply the whole vector here. So we have to consider it transposed as a row vector. So for the first equation, so obviously if we have 25 equations here, then we would have 25 rows. But our capital R is very small here in our example. It just has 2 rows because we have just 2 test assets. So the dimension, how many columns do we have? So we have so many columns as we have parameters here. Yeah? So we have 4 parameters in our parameter space, so we have 4 columns in each row of capital R. So where to find the first parameter estimate that we're interested in? Well, it's in the first column, or in the first place array of our vector. And where to find the next? Well, it's in the third array of our vector. So that's why we have here, this gives us the third position, and the first gives us the first position. Yeah, so very simple. It collects us, it indicates us where are the corresponding point estimates given in this vector here. So consider now the first vector b1 hat. And we know again b1 hat gives us the corresponding point estimates for the first equation here. And they are simply alpha 1 hat and beta 1 hat. And let's also consider a vector small r. Small r is just 1 and 0. And it gives us the corresponding point estimate in each equation. So in each equation, the intercept terms are collected, or they are given as the first point estimate in this corresponding parameter vector for each single equation. So now, what we can do now is we can use an identity matrix that has the dimension n by n, because we have n equations. We have n equations. So this guy here is the identity matrix of dimension n, and we use the Kronecker product for this vector here that we just defined, which is a 1 by 2 vector, giving us the corresponding, again, indicating us the position of where to find the intercept term. So what does that mean? The Kronecker product means that we have to multiply each element in the matrix here on the left hand side with what is on the right hand side. So and this is basically given here. So we have to multiply this guy here, this 1, with this vector here, 1 times this vector. We have here, the next element will be then 0 times this vector here, 0 times this vector, and so on and so forth. So what comes out then? If you multiply this out, and I recommend you doing this at home with pen and paper, it is our matrix capital R. So we can just rewrite our matrix capital R simply as the product of the identity matrix times our defined vector small r. It's just a trick to rewrite our matrix capital R. So, and what we also know is, if we multiply this matrix here with our vector beta hat, with this guy here, what comes out, what must come out, is the vector of corresponding point estimates that we want to test. Our alpha 1 hat and our alpha 2 hat, the intercept terms of this equation. So that is a trick to, it's basically this R matrix, this capital R matrix. If we multiply this capital R matrix with our vector of point estimates for our simultaneously equation model, it should give us the corresponding point estimates that we want to test. So that's the purpose of that matrix. So now we know what is our Q. We have defined it earlier. We know our beta hat. We know our R. And we see this R is obviously it enters the test statistic on many places here. So what remains obviously is to determine this matrix X wave, yeah, that we have also here. And this is what we want to do next. So the question arises, what about this X wave? How to estimate that? So let's remember now our regressor matrix X. What's that? It has the dimension t by 2, and it is a matrix that has in the first column vector a vector of 1s, and in the second column vector is just the vector of excess returns, denoted here as x1, x2 until x capital T. So our X wave matrix, it is a block matrix, okay? And it is defined as what you see here. So we have two equations, and on the main diagonal of that block matrix, we have our regressor matrix X. Yeah? So here we have a capital T by 2 matrix, here we have a capital T by 2 matrix, and the dimensions of the zero matrix here must be the same like the dimension of our regressor matrix X. Yeah? So this zero matrix is also a capital T by 2 matrix. Yeah? So it has just simply two column vectors, of zeros. So it's a T by 2 matrix consisting simply of zeros. So, but how can we construct this guy? Yeah? How can we construct this guy using linear algebra? So again, we use the Kronecker product. So what do we have here? It's again the identity matrix that has a dimension n. Yeah? Remember that this guy here is the identity matrix that has the dimension n because we have capital N equations. So we multiply the identity matrix that has the dimension capital N with the Kronecker product with our regressor matrix X. And again, what do we have to do? So we have to multiply each element here in this matrix on the left-hand side, which is the identity matrix, with what is on the right-hand side. And on the right-hand side, we have this matrix here, our regressor matrix, which has the dimension capital T by 2. So multiply this out. So 1 times this matrix here, 0 times this matrix here gives us 0. It gives us this matrix here, exactly what we want to need. And so on. Yeah? So on the main diagonal, we have 1s, because it's the identity matrix, obviously, multiplied with this regressor matrix gives us this matrix here, consisting of zeros. So only on the main diagonal, we have the corresponding matrix that we need, which is our regressor matrix, and above and below the main diagonal of our block matrix, we have blocks of zero matrices. So it's very simple to construct. So the dimension of our matrix X wave, this matrix here, this whole block matrix is denoted as X wave. So it must have the dimension what? Well, think about it. We have this matrix that has the length of capital T, and we have it twice. We have two equations. If we have 25 equations, we would have 25. The length would be 25. But since we have 2, capital N is 2, it's the dimension, the rows that we have is capital N times capital T, because we have T time series observations. And how many columns do we have? So it's obviously capital N times capital K. So the parameters times the numbers of equation. So that's also important to know. So now we know everything here. We know our each increment that we need for implementing our test statistic. So now we have all that defined. We have all this calculated. We just have to plug it into our program, and we will do this in Matlab, because it's very simple and very user-friendly. But you can, of course, use any program. That's up to you. I will show how to do this in eViews, in Matlab, and after that, we will also see how to implement this in a standard program such as eViews. So there are some methods, obviously, that are used in research that are basically mainstream. For instance, this methodology here, it's used in different contexts, not only in asset pricing and finance, but also in economics and in other researches related to social science. Yeah? But this pharma-make-best regressions, for instance, you will most likely not find in any standard software. So you have to program it by yourself. Yeah? But this methodology you will find also in standard programs such as eViews. Yeah? So once again, what do we actually have here? So, well, we know what is here. Yeah? That's a 2x1 vector, and that's just the vector of point estimates that we want to test. And it's basically this alpha 1 hat and alpha 2 hat. Yeah? So we have this on the right hand side of the test statistic. On the left hand side we have the same, but it's transposed. So it's a 1/2 vector. Yeah? So we have here a 1/2 vector times something in between times a 2/1 vector. So what comes out is a 1/1. It's a number. Yeah? It's a random variable. It's the realization of a random variable that we have. So, but what's that guy here? Yeah? I told you earlier that this must be a 2x2 matrix. And if you multiply that out, given the matrices that we have defined earlier, yeah, if you multiply this out, I recommend you doing this at home, what you will see is it gives you nothing else than the corresponding covariance matrix, yeah, of the corresponding parameter that you want to test. Yeah. So all this product here, yeah, which looks very, let's say, fancy, it's actually not that fancy. It just grabs you the corresponding elements in the covariance matrix that are related to the parameters that you want to test. So we have two parameters. That's why the covariance matrix must have the dimension 2x2, and you see here that's inverted. Yeah, so it enters the test statistic inverted. Yeah, so that's the estimated test statistic, yeah, lambda hat. Yeah? And we know, I told you already, it's chi-square distributed with 2 degrees of freedom. So we have to compare the random number, yeah, the realization of this test statistic. We have to compare it with the corresponding chi-square distribution with 2 degrees of freedom. And we know already how it looks like. It looks like that. Yeah, it is skewed here. Yeah, so the 95% probability will be something like here. So whenever this test statistic here falls into the critical area, so on the right hand side, so it is larger than the value corresponding to the 95% probability, given we have a significance level of 5%, which we usually use in finance research or in economics research, then we would reject the null hypothesis, and in turn it would imply that our model here is not able to price the test assets here correctly, because the intercept terms would be jointly statistically significantly different from 0. Okay, so that's what we have to do. But the question arises, why do we have to use a chi-square distribution with 2 degrees of freedom? So we have to remember from statistics that a sequence of squared normally distributed random variables follow a chi-square distribution. Yeah? So we have here obviously two parameters, yeah, that are squared. You see, the first guy here, it's multiplied with itself here. Okay, it's squared, and the same is true for the second guy. Yeah, so we have to basically build a scalar product, and then there's something also in between. So we have the sum of alpha 1 hat squared plus alpha 2 hat squared. Yeah, but we have somehow here, this is in between, and that's sort of, you can think of it as the normalization, yeah? Because we divide it here, obviously, or we have the inverse of the covariance matrix in the middle, in between, yeah? And that corresponds, or you can think of it as a kind of normalization. So the point estimates here are standardized Yeah? So the sum, what we have is the sum of squared standardized normally distributed random variables. Okay, since the point estimates of the OLS framework are per definition normally distributed, at least when the sample is large. And this operation here, what it does is it sort of standardizes the squared normally distributed random variables. Okay, so that's why under the null hypothesis, if the null hypothesis is true, this expression here is distributed as chi-square with 2 degrees of freedom. Yeah, so one thing that you have to bear in mind is, so all these methodologies that we discuss or that are usually used in finance research or in economics research, they are usually only valid when the kurtosis exists. So the input variables here, our market factor, test assets, and if we have here more risk factors, so these guys, they have to have a kurtosis. It must be finite. If the kurtosis is either infinite or doesn't exist, what happens then is that our point estimates become sample specific. Okay, so the t statistics actually doesn't mean anything. So this is something that you have to have in mind when you operate with these kind of equations. For instance, if you think about the Farman-French 6-factor model, what's the 6th factor in that model? It's the momentum factor, exactly. And the momentum factor, we know already from many research papers that the momentum factor sometimes has its crashes. Okay, you can sometimes lose 30-40% of your money in only 1 month. So you have these huge crashes that typically occur when the market was in a bear market, in a downwards trend for some time, and then bounces back. So then momentum crashes. I recommend you the paper Momentum Crashes. There it's basically well written. So the kurtosis of momentum is much higher than 3. Yeah? So if we would have normally distributed random variables here, then the kurtosis of our input variables would be 3. Yeah? And our methodology works fine if the kurtosis is less than, let's say, 4.2. If it's less than 4.2, it converges in large samples towards normal. But if the kurtosis is 15, then this methodology and any other methodology becomes problematic. One final question. So let's say again we have this standard model framework here. We have 2 test assets and here 1 regressor, 1 risk factor, the market factor, and let's say we want to test the beta exposure instead of the intercept term. Yeah? We want to know if the market factor, if the market factor matters. And in this time series framework, we would basically test the exposures against the market factor, our betas, jointly across all test assets. So if we have 25 test assets, then we would have 25 parameters to test jointly. So how would we implement our test statistic here? Yeah, everything remains the same. So the only thing that changes is our small r. Well, you remember previously we had a 1/2 vector indicating us where the corresponding point estimate is located in each single equation. Yeah? If we have the same model framework, but we are interested in testing the exposure against the market factor, okay, the only thing that changes is our small r. Yeah? Now it's 1/2 vector where the first element is 0 and the second element is 1 because we're interested in this guy here. So everything else from our derivation remains the same. So you can also think about how to extend this model here. If you have more regressors here, obviously this guy here becomes larger and the other matrices need to be defined or redefined accordingly. Yeah? So this is something that you might think about. We will now next we will implement this methodology in Matlab, and we will do this using 25 test assets. Yeah, so our capital N is then 25, and we will use the Farmer and French 5-factor model. Ladies and gentlemen, we will now learn how to implement this multiple equation model that we discussed on the whiteboard in a computer software called Matlab. So again, this is how it looks like. That is the command window once you open Matlab. Here on the left hand side we have the workspace, and everything that we do in the command window, every command that we plug into Matlab will appear, the corresponding matrix or vector will appear here in the workspace. So let's start with opening a script. So instead of using the command window, we will write our script here into this page here, and then afterwards we will copy the whole commands here into the command window, and then we will let it run. So first of all, let's import some data. Here we push the import data button, and we will import data from the desktop, and here we have the folder Farmer Macbeth. I have already used this data for showing how to implement Farmer Macbeth regressions. This is the same data set. So let's say we want to investigate 25 test assets sorted by size and profitability. And we will use test assets using European stocks. And these test assets are given in gross returns. Let's double click here on this Excel file, and we will upload it here automatically in Matlab. So here's what you see. Here are 25 column vectors, and each column vector denotes the gross returns of 25 stocks sorted by size and profitability for the European market. So we see here we have 351 observations. The data matrices for the risk factors don't match up, so we have to get rid of one observation here so that we have 350 observations. Let's upload it as a matrix. If we would choose column vectors, we would have 25 column vectors in our program, but we don't want that. We want the whole matrix here. Push the OK button, and now if we push away this import wizard, we will see here it appears to be a D by N matrix. We see here's the dimension, here's the minimum and maximum value of that matrix, and we see we have 350 time series observations and 25 test assets. Now, let's rename it. Let's denote the matrix as capital Y1. Okay, capital Y1 again collects our test assets in gross returns sorted by size and profitability. Let's also import the matrix of risk factors. We have it here, Europe risk factors, yeah, and now we have to remember this is small. We have small spread size. We have small spread risk factors. Yeah, our data matrix looks like this. We have the European market factor in excess form. That's the first column vector here. In the second column vector, we have the size factor for the European market using European stocks. We have here in the third column, we have the value factor denoted as HML, high minus low book to market ratio. And we have here the profitability factor and the investment factor. In the last column, we have the risk-free rate. We don't need it in the factor matrix. Yeah, we just skip it. And now it's important to remember that the investment factor and the profitability factor, these guys here, they have widened spread. Yeah. So we have small, in our paper that is entitled Choosing Factors, the International Evidence, which I wrote together with James Kolari from A&M Texas University. What we do is we basically replicate and slightly modify the results reported in Farmer and French paper from 2018, Choosing Factors, but we implement the methodology for the European market, the Asian Pacific market, excluding Japan, the Japanese market, and the North American market. Yeah? And what we do is we implement small spread risk factors for investment and profitability using just small stocks. Yeah? If we just use small stocks, obviously these spreads are wider, as if we would use the whole stock universe. So again, let's upload this matrix here. It's a 350 by 5 matrix. So again, we have 350 time series observations and 5 risk factors. Let's import this. It appears now here in the workspace again. Let's rename this matrix here as factor matrix, denoted as capital F. Let's also import separately the risk-free rate, because we need that. It's again here is in this data matrix, in this Excel file here, and we know it's in the last column here, the risk-free rate for the European market. Let's import it here. Let's denote it as RF, small rf for risk-free rate. Okay, so now we have our data matrices defined. We can now move on and implement our test statistic. Again, what we want to do is we want to test if the intercepts or the alphas, okay, are statistically significant. So this test is often referred to as GRS-test, okay? So because if the alphas, if the intercepts are jointly statistically significant, it means that the asset pricing model cannot price our test assets correctly. Okay, so if the test statistic is statistically significant, it means that the pricing errors, there are systematic pricing errors going on, and our factor model is not able to price these test assets correctly. So we need a different pricing model, simply speaking. So let's define first our time series dimension, capital T. It's the length, it should be the length of our risk-free rate vector. Yeah? And we know it's already 350 time series observations. We could also write length of y1 or length of f, it doesn't matter, because obviously we have in every matrix or vector here the same number of observations. It's 350 time series observations. So we have 25 test assets. Let's define the number of test assets as 25. You remember from the whiteboard we had only 2 test assets, so capital N was 2. Okay. Also remember from the whiteboard we had only one. We had the capital. We are considering the capital as a pricing model where we have just one risk factor, which is the market factor. So we had K is 2 because we had 2 parameters in each equation. Yeah. So we had 2 equations. N was 2 and K was 2 because we had only 2 parameters to estimate, which have been the intercept term alpha and the loading against the market factor beta. But here in this case, we have 5 risk factors plus the intercept term, which is 6. So the parameter space corresponds to capital K is equal with 6. Let us define now the excess return matrix. Yeah. So Y is the excess return matrix. Yeah. And how is it defined? So it has the dimension. So first we have to decode a zero matrix where we plug in the corresponding excess returns. So it should be a zero matrix which has the dimension capital T by capital N, right? We know this from the whiteboard already. So for I is 1 until capital N, so in each column vector, what do we want to do? So each column vector of our matrix Y, yeah, so each column I in my matrix capital Y should be what? It should be equal with the entries, with the corresponding time series vectors in our matrix Y1. Okay, remember now that we have here the column dimension, I is here the column dimension. You could also write here J, doesn't really matter. Let's use the index J here for the column dimension, and we subtract the vector of risk-free rates. And we do this for each column J. Okay, and we have 25 test assets. So this loop here runs from 1 to 25. We end this for loop, and what we'll have then, if we run the code, you will see we can already copy it. Let's copy it and plug it here into the command window. So what we see here now in the workspace, if we double click this matrix here, it will basically give us the corresponding XS return vectors of our 25 test assets. Yeah, very simple. We can also plot. Let's say we want to plot the XS returns of the first test assets. It's simply the command plot. Plot from what? Well, take the whole columns from the take all rows from the column number 1, and plot it. So that's basically the corresponding command in Matlab, and here's how it looks like. So this is our this is the time series evolution of the XS returns for stock number 1 or test asset number 1 in our XS return data matrix. So let's move on here with our code. So what's next? What do we need also for the test statistic? So obviously we have to run. You remember we have to run 25 regressions for single equations here for each test asset. So what's the regressor matrix X? X should have a vector of ones. That has the dimension capital T by 1. That's our first regressor in the regressor matrix. And here, this parenthesis here define the matrix. So we plug into this matrix here. What do we want? Well, we want to have a vector of ones. And what else do we want? We want our data matrix of risk factors. And we know this. The dimension is here. We see it from the workspace. Is 350 by 5. So we have the correct dimension here. So what we'll have here, the X matrix, if we copy it here into Matlab, you will see here, this is our matrix X. It has 6 columns, and in the first column is a vector of ones, just as we defined. So then we want to store in each regression, for each single equation, we want to store the corresponding point estimator, the vector of point estimates. We want to store it in a big vector, and you remember from the whiteboard we denoted this vector as beta hat. And here in our notation in Matlab we call it capital B underscore hat. So this is our long vector that has the dimension k by n times 1. So this is a k times n by 1 vector. Because we have for each test asset, we have capital N test assets, we have 6 parameters, so capital K parameters. So this guy here needs to be a capital K times capital N by 1 vector. So, and here we have to define it first as a zero vector of the dimension. Let's see. We do not define the dimension. Actually, we could define it, but we just define it as empty matrix. So this is an empty matrix here in Matlab, and it means that we can store that we can, in each loop that we define, each for loop that we define now, we will store something here in. That's a very easy way in Matlab how to create either a big matrix or a big vector. So there are always different ways how to implement things, and this is just one way, one easy way how to do it here. So we also wanted to have a matrix of where we store the corresponding residual vectors of each regression equation. You might remember that from the lectures. We need this the covariance matrix from the residuals, right? That was the important thing here in our multiple equation models. Why? Well, because the equations are correlated, and that's basically captured in the covariance matrix of the residuals for each equation. So we store here in our capital E matrix, it should be zeros, and we have capital T time series of observations, and we have capital N vectors. Yeah? For each equation, we have one residual vector. So this is what we will store in here, in this matrix, capital E. What is next? We want also to define our small r, the vector, where we basically determine where to find the intercept term in each equation, yeah, for each single asset. So it's the first element. Yeah, remember that. So the second element was the market factor in excess form. The third element was the size factor. The fourth element was the value factor. The fifth element was the profitability factor. And the last element was the investment factor, right? But we were interested in the intercept term, and that's the first element, the first parameter. Yeah? So that's the small r. What else do we need for our formula? You might remember that. Hopefully you made your notes, the lecture notes. You might now compare with what we have done on the whiteboard. So next we want to run a regression, a single equation model regression for each single asset. Yeah? So again we operate with a for loop. For j is 1 until capital A, what should we do? So let's estimate this small b hat. Yeah, so that is basically the point estimator for each single equation, and we know it must have the dimension 6 by 1, right? So, and what should it be? We know this from standard econometrics class. It's x transposed times x, so the regressor matrix transposed itself, inverted times the regressor matrix transposed, right, times what? Times the corresponding vector of excess returns for asset j. Yeah. So in the first loop, we grab the first test asset. In the second loop, we grab the second test asset, and we do the same regression again, and again. But always, of course, we get different exposures or loadings, point estimates, yeah, for loadings against the risk factors, right? So then we have our E hat, yeah, so that's our regression residuals, the estimated regression residuals, and they are defined as what? Well, it's the dependent variable, right, the corresponding dependent variable minus what? Minus the estimated vector, and that's defined as capital X times the parameter vector beta hat, right? So that's our estimated vector of excess returns. Yeah, this is our y hat. Yeah, this is our y. This is our y hat. Y minus y hat is what? It's the residual e hat or u hat, depending on how you have to find it. So, and what do we want to do? First of all, we want to stack this point estimate here, our beta hat, for each single equation, wherein herein, in our capital B underscore hat. So capital B underscore hat should be what? It should be what it is, yeah, and that's just an empty matrix, because this is what we have defined outside the loop. Yeah, it's an empty matrix, and we add what? We add our B, small b underscore hat. Yeah, what we have just estimated here. Yeah, this guy here. And we do this for each run. Yeah. So in the first run, when j is 1, we add the first vector of point estimates, and then in the next loop we add simply the next point estimator, and so on and so forth, without overwriting anything here. Then also we want to store in our empty matrix E the corresponding vector of residuals, the estimated residuals. So for all rows in column J, do what? Put in the corresponding E underscore hat, the estimated residuals. Yeah, that's what we have to do, and that's obviously overwritten, yeah, because here we have no index, so that's overwritten, and this is also overwritten. The point estimate vector and the residual vector are overwritten in each run, and just stored either in this guy here or in this guy here. Very simple. Then we end this for loop here. What do we need next for implementing our test statistic? You might remember we need the corresponding covariance matrix of the residuals of this guy here. We have stored them here. And we know very simple in Matlab, we have the command, we can code it very simply. Again, there are different ways how to do that. So we can do it like this. We can code a zero matrix first, and we know the covariance matrix must be n by n. Yeah? And we can first code a zero matrix where we store the corresponding variances and covariances. So for I is 1 to capital N, and for j is 1 until capital N do what? So sigma ij, the corresponding element in the covariance matrix, should be what? It's the corresponding elements. Take the vector I from our matrix E, yeah, transpose it. So now our t by 1 vector becomes 1 by t, and then just multiply it with what? With corresponding element j. And then we have to divide it also. We have to close this parenthesis here. And we can divide it by the number of observations, capital T. Then we end this loop. And that's it. So let's do that. Yeah, let's copy here everything into Matlab. So that's our sigma here. You see, the first element in our sigma is 0.8738. Yeah, and so on. So that's a 25 by 25 matrix. So on the main diagonal, we have the residual variances for each regression equation. Yeah. So, and here, this element here, for instance, element 1, 2, this would be the covariance between the residuals from the first and the second test asset. Okay. And so you can go through the whole covariance matrix. Another way how to implement this matrix here would be simply by writing covariance from what? From the matrix E. We can define sigma, or let's define it as sigma 1 as the covariance. And now we write it here into the command window directly, right? You see that we can define the matrix sigma 1 as simply the covariance of our E matrix. And now what should pop up here? The first element should be, you might remember, it should be 0.8738. Yeah. So do that, and you see here it's pretty much the same. Yeah. So this is another way how to do that. Either we write directly covariance from E, or we code it step by step. Yeah. So both ways are possible. So what do we do next? You might remember we need the matrix capital R. Yeah, capital R. And we have defined it as what? As the Kronecker product from what? The identity matrix of dimension capital N and our vector R. Yeah. So that's very simple. So you might remember now each element here on the left hand side is multiplied with what is here on the right hand side. That's the definition of the Kronecker product. Yeah. So we have here already defined our R, so everything should be in order here. So what do we need? What's the next step in our multiple equation model? So you might remember from the whiteboard derivation, we also need the matrix X wave. Yeah, the X wave matrix, this huge block matrix. And we define it here as simply as XX. And it should be what? It should be the Kronecker product from what? From the identity matrix, again, from dimension capital N, yeah, because we have 25 test assets, and what? Our regressor matrix X. So that's what we have defined. So, and now remember here, that is our X wave. We called it X wave on the whiteboard. Yeah. So what else do we need for our formula? So you might remember from our null hypothesis, we needed we have to define what we test, and want to test if they are equal to zeros, if the alphas are equal to zeros. Our Q, the Q from the whiteboard, you might remember, it was a vector, it was an n by 1 vector of zeros, yeah, due to our null hypothesis. So our Q should be a vector, simply a vector of zeros. Yeah, n by 1 vector of zeros. So next, we want to define the inverted matrix. Let's define the inverted matrix of sigma. You might remember that we had in the middle of the test statistic, we had the covariance matrix sigma, yeah, from the residuals, but it was inverted. Yeah? So let's define the inverted covariance matrix as sigma underscore 1. And what should it be? It should be sigma to the power of minus 1. Yeah? That gives us here the inverse of our matrix sigma. So then, what else do we need? So we had in the middle of the test statistic, you might remember that we had sigma hat inverted times the identity matrix of dimension t, right? So that was how it looked like. So we have to define that matrix, this huge matrix. Let's define it as Q. Q should be what? Compound the Kronecker product from sigma underscore 1 and the identity matrix. Right? That is how the matrix was defined. So yeah, now remember, we had earlier, we had here, yeah, the identity matrix of dimension n, and it was on the left hand side. So each element here we are multiplying with what was on the right hand side. Now we have here the inverse of the covariance matrix for the residuals on the left hand side, and each element is multiplied with an identity matrix of the dimension t, and this is exactly how it should be. So now let's implement the test statistic. It's called lambda, actually lambda hat, according to what we had been written on the whiteboard, and it was defined as what we had. Now we have to remember it was capital R times beta hat, and it was in our notation here in Matlab, capital B underscore hat minus Q, right? It was transposed times what? Now we have here 3 points. It means continue the command in the next row. So it was, and then we had this term in the middle, capital R times, then we had again parentheses open. It was what? It was this X wave. In our notation it was XX, and it was transposed times Q, right? Times what? Times X wave. This guy here was inverted times our capital R matrix, and this was transposed, right? And the whole term in the middle was inverted. Let's continue the command in the next line. So, or we can actually continue here. We have still space times what? Yeah, times the first term here. Yeah, that collects us the corresponding alphas. You might remember that, what we derived on the whiteboard. Yeah. So that's everything. Now we should be ready. We have now implemented everything here. And here actually we can take away this parenthesis, right? So always when there's something wrong here, then Matlab will give you here something in red, and then you know we have to check up one more time what you have written here. So now we have implemented everything. Let's copy everything into the command window and see what comes out. So now our lambda hat is now here in the workspace. So what is it? It's 121. So you have to remember now our test statistic is distributed as chi-square distribution under the null hypothesis with 25 degrees of freedom, right? So we have to compare this guy here, the value of the test statistic, which is a random variable, with the corresponding critical value of the chi-square distribution with 25 degrees of freedom. And we have some tables, of course, for that, which is here, for instance. Here's one table. Let's just check it. This is the chi-square distribution. Here we have the 95% probability, and it is, you see, for each degree of freedom, it's increasing. Of course, it must be like that. So you know the chi-square distribution is skewed, yeah, to the left. And here, if you want to have the critical value for the 95% probability mass, it is given here. This means that 5% of the probability mass is on the right on the right tail of the distribution, right? So, and 95% correspondingly on the left. So we have to scroll down here. 25 degrees of freedom, we don't even have it here. We have only 24 and 26. Let's take the value for 26. It's 38.89. So, and our 121 is obviously much, much larger than 38. Yeah, so it falls into the critical area, which means that we have to reject the null hypothesis. Yeah? It means that our Farmer and French 5-factor model obviously is not able to price the test assets correctly. Yeah? Now remember again, this is a joint test. This multiple equation model is used for joint tests. Yeah? So what else can we say? We could also test now, okay, we could use the same model here and test if the market exposures are jointly statistically significant. How would we do that? You might remember from the whiteboard, we just have to move this to the next. Yeah? Again, here in this small r, it's indicated which parameter in each equation we want to test. Yeah? And so this test is constructed in a way that we test the same parameter in each equation, yeah? The corresponding parameter in each equation. In the first run, it was the intercept term that we have been interested in the cross-section, yeah? Jointly for all test assets at the same time, and now we do the same for the market factor, which is on the second position. Okay, that's all we wanna. That's all we have to do. Everything else remains the same. Now, that's the nice thing with this testing framework. Again, we just need to copy everything into the command window. Voila, what comes out? Our lambda is now even larger. It's 7,000, right? Well, yeah, it's 70,000 actually. It's 7 to the power, and there's like 5 after the, it's like this. 7 and 0, 7, 6, 1. So it's 5 behind the comma, so it's 1, 2, 3, 4, 5. It's 70,000, right? Isn't it so? It's 700,000 actually. So it's a huge number, obviously, and we know already, we reject the null hypothesis. It means that the market factor jointly matters. The market factor is statistically significant in the cross-section of our test assets. It's jointly significant on any level. We can do the same thing now for the size factor. Let's test the size factor jointly. Is the size factor jointly significant in the cross-section of assets here, of our test assets? So again, we move this here one to the right, and we just copy everything. Everything is overwritten and re-estimated for the size factor. And even the size factor, you see, it's statistically significant. The test statistic is 36,000 or something. So it's highly significant. Even the size factor matters cross-sectionally. Because the beta exposures are jointly statistically significant. Let's also do the same for the for the investment factor, which is the last guy here, right? We know from the Farmer and French paper choosing factors that the investment factor basically doesn't matter, or it was actually the value factor, right? It was this guy here, the value factor that didn't matter. Oh no, the value factor we find, it was the fourth guy, it was this guy here, right? This guy, that's the value factor. And this guy here doesn't matter in the US. However, in our paper, we found that it's the investment factor that is the guy that probably doesn't matter. It's the value factor that matters, actually. So let's test the investment factor. In our paper, we were using a different test. Yeah, we will see that when once you read the paper, you will understand that this was a different test. Now we're using test asset. We use the GRS-test. In our paper, choosing factors, the international evidence, we were using a test for nested models, right? So that's a different test. But here, what we will see is a different result. So if we use now the GRS-test and want to investigate if the investment factor matters, yeah, so does do the beta exposures against the investment factor matter jointly? So this is the test basically, and we will see the test statistic is 56. Yeah, it's larger than 38. So in this cross-sectional test, the investment factor seems to matter. Yeah, the investment factor seems to matter. So this was basically how what we can do in our cross-sectional framework here. Yeah, let's do what we have done on the whiteboard. Let's redo this test. Yeah, let's import a different data set. So let's say we want to test the additional risk factors of the 5-factor model, which are the investment factor and the profitability factor, against the 3-factor model. How would we do that? So let's now our matrix of dependent variables. It's not any longer the test assets. Now we have to use the risk factors itself, right? So let's just, we can do it now in different ways. Actually, we don't even have to do that. We don't even have to upload them again. So we know, let us define. Yeah, we go back to our script page. Let us just define our matrix of excess returns, our test assets, as what? It should be the rows 4 and 5, right? The rows 4 and 5 of our factor matrix, right? Because we know that in our factor matrix, let's go back here into our workspace and scroll up a little bit. We know here the row 4 and 5, here is the profitability factor and here is the investment factor, right? We know this already. So, okay, let us define the test assets that we want to test as the columns 4 and 5 of our factor matrix. So then we have to redefine our regression matrix, and it's now what? Again, we need a vector of ones, but then we need only the vectors 1 to 3, right, from our factor matrix, because we know in rows 1 to 3 from our factor matrix, there are the corresponding, here we have the market factor in excess form. Second column we have the size factor. Third column is the value factor. Okay, so that's what we define here. Then everything else, our R of course changes because our parameter space is now, it changes as well. Our parameter space is now what? It's now 3, right? K is now 3 because we have only 3 parameters in each equation. And let's say again, what do we want to test? We want to test this guy here becomes now a 1/3 vector. We want to test the intercept term. And each equation for each test asset, and each test asset is now, we have only 2 test assets here, so n is now 2, capital N is 2. So we have 2 test assets here, we have 3 parameters, and we want to test if for the investment factor and the profitability factor, if the intercept term is statistically significant. If the intercept term is statistically significant, it means that the 3-factor model is not able to price the additional risk factors of the 5-factor model. In this case, we would say that the 5-factor model is the correct model in this framework. So what else do we have to do? We have to do nothing more than that. Everything else here remains the same. So we can just now copy everything. Copy it here into our command window, paste it in. And now obviously, we have to define. Now let's see where things go wrong. We have to define, let's check our X matrix here. How does it look like now? It's a 1/4 matrix. Yes, of course, it's a 1/4 matrix. So this guy here, because we have the intercept term is the first guy, second guy is the market factor, then we have the size factor, and then we have also the value factor. So this guy here changes, right? It's 4. Capital case for the parameter space is 4. So, okay, this was the error. Let's again copy everything and put it into the command window. So what's our lambda now? We see our lambda is 52. So it means that we would reject the hypothesis that the null hypothesis, which means that the Palmer and French 3-factor model is able to price the additional factors of the 5-factor model correctly. Hence, we would reject the 3-factor model in favor of the 5-factor model. So this is basically what it implies. And moreover, the test statistic is now distributed as chi-square distribution with 2 degrees of freedom. So we have to check. This is the corresponding value is 5.99. Okay, and our test statistic is 52.81. So it's much larger. So we clearly reject the null hypothesis. So this is basically how we would proceed. We can play around with this. We just have to make some changes here in the code, in the definitions of our dimensions and of our matrices, and then we can use the same code for many different research setups. Thank you.